Okay, so we had talked about how we have energy, and it's really energy has this waveform, and we had said that it has a wavelength that you can measure, and you probably have heard of quantum mechanics and all of this stuff with Einstein and some other physicists who who realized that energy, especially as acts kind of like a particle and sometimes like a wave. And so we've got this thing called the wave particle duality, and it says that as an object gets larger, it becomes more like a particle. When it's very, very small, it's more like a wave. So it's like a particle. I mean, actually, the packets of energy that come from the sun that are in the visible light range, we refer to them as photons. And photons are a particle with no mass, which again, it sort of defies logic to even say that. But anyway, so we have this energy wave, and I just realized I was getting ahead of myself, so I'll come back to this in a minute. I want to talk about this picture right here first. Before we get into this, all this business about understanding the energy waves, we need to know what percentage of the different intensities. We said that short wavelengths have much higher energy than long wavelengths. So when we look at the radiation from the sun, what we find is that the visible light, the stuff that you can see, is this shaded area in here, and that's 39% of the radiation that reaches to Earth. 53% of it, so basically what we have down here is we have very short wavelengths at this end of the graph and very long wavelengths at this end of the graph. And so here we have the visible light here, and we'd said that's 39%. Then the really long wavelength stuff, it's 53% of the energy that reaches the Earth. And this was then the infrared kind of stuff, the thing, heating of the Earth, the radio waves and microwaves. And then we have the stuff that can be dangerous, the ultraviolet, X-rays, and gamma rays, the short stuff. It's only about 8%. Okay, so to get back to the point, what I was thinking about when I started talking here in this little video, I was talking about this wave-particle duality thing. And so energy versus mass, and you may have seen this right here. E equals mc squared. Now, I mean, everyone knows, or you've probably all are familiar with that, and you say, oh, that's something to do with Einstein, his theory of relativity, right? But you might not know what it stands for. So these letters stand for stuff. The C, that's a constant. It's the speed of light squared. I don't care about that because I'm not doing math here. But what about the rest of it? E is energy. M is mass. So what does that mean? That means that energy and mass are interchangeable. They can convert back and forth. And you and I see that all the time when we put mass in our car, gasoline, and we convert it into energy, we drive down the road, and then it's gone. Mass became energy and got used. And you got to add some more mass. You got to go get some gasoline. So it's not as crazy sounding as it seems, this business of energy and mass being interchangeable. And with these, when we are trying to understand this wavelength, we can think of it as either kind of particle-like or as a wave. And so you can think of them either way. Okay, so ultraviolet radiation. We have all of this radiation, and it might seem really terrible when we think about it. We'd said that stuff's dangerous. And the ultraviolet radiation that is closest to the visible light, that would be this part right here. We'd said the shorter your wavelength, the higher the energy. So that would be lower energy ultraviolet radiation. That would be UVA. And then as we move a little bit further away, shorter, it becomes UVB, and then it becomes UVC. That's the highest of the highest energy ultraviolet energy. And it does really it destroys, breaks chemical compounds apart. Now, what happens though is we have this atmosphere. We were talking about it last time, and the molecules in the atmosphere are what protect us from this high energy ultraviolet radiation. And so we're going to talk about how the two really high energy radiations, they don't make it all the way to the surface of the earth. Ultraviolet C, the highest energy ultraviolet radiation, interacts with oxygen in the atmosphere, and it forms ozone, water in the atmosphere, and it breaks it apart and produces ozone. And so the energy that it's carrying is being used in the atmosphere, and so it doesn't make it to the earth. Now UVB, some of it's going to also be interacting with molecules and giving up its energy in the atmosphere, but some of it does sometimes make it all the way to the earth. But the low energy stuff, the ultraviolet A, that is the one that makes it to the earth, and that we actually have to contend with when it comes to the damaging effects of ultraviolet radiation. So we'll talk a little bit more about that, I think, next when I come back.